Hi everybody, welcome back. In this problem, we're going to go ahead and calculate a drug regimen for the scenario of an intermittent infusion. So here's the case scenario. You need to prescribe a patient drug X, which is given as an intermittent infusion over 1 hour. The pharmacokinetic parameters for this drug are as follows: 0.098 hours to the -1 for the elimination rate constant, and the volume of distribution is 14.2 liters. Your desired concentrations for this regimen are to have a max at steady state of 5.4 milligrams per liter and a minimum at steady state of 1.5 milligrams per liter. So as we talked about in other videos, again, you have highs and lows. And what we want is a high of 5.4 and a low of 1.5. So what do we need to calculate a drug regimen? Well, we need a dose and an interval. So when we do these calculations, we always start with interval because we need that to calculate the dose. So let's do that for an intermittent infusion. And an interval is always very similar. They always have this first part of the equation. So ln natural log of the max concentration minus the natural log of the minimum concentration over the elimination rate constant. But for intermittent infusions, we tack on T prime. So let's figure out what the answer is here. And what we have here is the natural log of the 5.4 minus the natural log of 1.5 over 0.098, the elimination rate constant, plus an hour, which is what we're infusing the drug over. And if we calculate this out, this equals 14.1 hours. However, 14 is not really a typical dosing interval we use. So this could be drug and context specific, but we usually round it to a more natural interval that we see, like 12 hours. So let's say that's what we decided here, 12 hours. So with that information, let's go ahead and calculate a dose for this intermittent infusion. And a dose in this scenario is an infusion rate. And it's a little bit longer of an equation, but it's CSS max times elimination rate constant times the volume of distribution times 1 minus e to the negative elimination rate constant times the interval and the numerator, and in the denominator it has 1 minus e to the negative rate elimination constant times T prime, or the infusion time. So let's plug in what we have. And what we have here is the 5.4, which is our CSS max, our elimination rate constant, our volume of distribution, which is 14.2. And then in the numerator, we have, again, a rate elimination constant, and 12 hours, which is our chosen interval. And then that's over 1 minus e to the rate elimination rate constant again, times 1 hour, which is our infusion time. So putting this all together, we get 55.7 milligrams, and we get that because the liters cancel out here, and then the hours also cancel out. We're left with milligrams over hour because this is an infusion rate. We might be able to put this into an IV bag and give it to a patient, but many times this will be rounded to a more friendly number, 50 milligrams per hour. So we would give this patient 50 milligrams per hour every 12 hours infused over an hour. So what if we wanted a loading dose? We wanted to get this patient up to therapeutic concentration quickly. Well, we can do that with an intermittent infusion as well. And that's simply the infusion rate that we calculated over 1 minus e to the rate elimination constant times the tau we calculated. Putting that in, that gets us to a load of 72.3 milligrams Again, probably rounding to a more friendly number, gives us 75 milligrams per hour, could be given as an initial infusion of 75 milligrams per hour to help load the patient up. You can tell how it's higher than our chosen dose here, so we'd probably start with this infusion because most infusions need to be given over a certain amount of time. You can't just push a drug. And then we'd go to the subsequent 50 milligrams per hour on all subsequent doses. That gives you an idea of how we calculate a drug regimen for an intermittent infusion. Thank you for your attention.